By making two assumptions, we can produce a very elegant sorting algorithm. That the numbers are non-negative integers. The range of values is known. For instance, we could be given this list and told the numbers range anywhere from 0 to 9. We will construct a list that is the size of the range, in this case 10. We can call it the placement array. The indices will range from 0 to 9. All the values can be initialized to 0. The goal of the placement array is to tell us where each number should go in the final sorted array. For instance, right now the number 7 should go at position 0 according to the placement array. This is because there is a 0 at index 7. If we let R represent the size of our range, our auxiliary space complexity so far is big O of R, as we have just added R units of storage. The first step to make the placement array work is to store the counts of each number at the appropriate index. So we simply go through the array and add 1 at the corresponding index. If n is the size of our original array, then so far our time complexity is t at n is big O of n. The next step is to accumulate the array, meaning adding the value at every index to the next one. Before, our time complexity was big O of n. However, now we have looped through an array of size r, meaning our time complexity is now big O of n plus r. Is the placement array accurate now? Well, for instance, it says 1 should be placed at position 2. In fact, 1 should be at position 0 and the second at position 1. It also says that 2 should be at position 3, when in fact it should be after the two 1s at position 2. What the value in the placement array is really telling us right now is the position of the next value. If you think about what accumulating the array does, this should become clear. To correct for this, we must shift all the values 1 to the right. Now the result array can be created, which will store the sorted values. It should be the same size as the original array, of course. We have just added n units of storage, so our space complexity is now big O of r plus n. Now let's go through the array element by element. 5 goes at position 4. We must increment this value in case there's another 5. 7 goes at position 6. 5 goes at position 5. 4 goes at position 3. 8 goes at position 7. 1 goes at position 0. The next one now goes at position 1. And 2 goes at position 2. We now have a sorted array. The final time complexity was big O of r plus n. The final space complexity was big O of r plus n. This sorting algorithm is not in place, as it required additional storage, the placement array and the result array. This sorting algorithm is stable, meaning that elements with the same value maintain their original order. This is best understood if you color the array. The algorithm is not comparison-based. There is never any comparison between two elements in the array. We will write this algorithm in Python starting with some pseudocode. First, we create our placement array of size r. The placement array will be filled with the counts. The placement array will be accumulated and then shifted using functions we'll define at the end. The result array will be created. Elements will be put in the result array based on positions indicated in the placement array. Finally, the result array will be returned or outputted. Here is the definition of the accumulate function. Here is the definition for the shift function. Thank you very much.